All right, this is lecture 18 of ECE402. This is another lecture that's related to fixed waveforms, but in this case, we're doing what we called spectral matching synthesis. So what we're doing is we're taking several fixed waveforms and adding them up. So it's a kind of additive synthesis, except that instead of using pure sine waves for each partial, forget that idea. Instead, what you have is basis functions. So you have some number of fixed waveforms. In our example today, we're going to have 3 fixed waveforms. Each one of those fixed waveforms corresponds to a phase oscillator with a wavetable. And so you have 3 phase oscillators. They're all going at exactly the same frequency, but at different amplitudes, at time-varying amplitudes. So basically what you're doing is you're taking these 3 fixed waveforms, adding them up different ways, and getting different spectra that way. Because each fixed waveform has its own spectrum, and by having more of one and less of the other, changing over time, you get a time-varying spectrum. I was getting stir crazy at home, so if you're hearing frogs or birds in the background, yeah, I'm in beautiful central Illinois. The floods receding from the Sangamon River. In any case, I had to get out of the house, so here I am. And how did I have this balanced? There we go. Okay. So now, yes, so this is a kind of additive synthesis. And it's also the topic of the next homework that's due on Tuesday before lecture. So Tuesday before 8 a.m. So what is the procedure here? We start with the original sound, so some recording, generally of a single note, because once we've done this analysis, we can change pitches on it and that sort of thing. So what we do is start with an original sound with an original single note and do a pitch tracking Fourier analysis, or what in this class we've been calling short window method. Then we do a time-varying spectrum analysis. The pitch tracking Fourier analysis gives us the time-varying spectrum, which we call a series of frames for today's lecture. So these frames, they just correspond to a little windowed part of the sound, or if you like, a grain of the sound. It's as you know, for a short time analysis, short window analysis, we've been using 2-period windows. So you have a whole bunch of these 2-period windows. Each one of these 2-period windows on the sound corresponds to a spectrum, right? You could take a Fourier transform of each one of those, and that corresponds to a spectrum. So you can think of them as a series of frames, or a time domain, a series of grains of sound, or you can think of them as a series of spectrums that change over time. What the idea then is, we're going to pick 3 of these frames, or 3 of these spectra that we have, and call them our basis spectra. We're going to just pick 3 representative ones, and if we pick 3 good representative ones, we can put amplitude envelopes on those 3 wavetables, and or those 3 spectrum, you can think of it either way, to synthesize a whole thing. So what we're going to do then is do a matching procedure, which in this paper, what we're interested in is genetic algorithm, or GA search, which we'll talk about a little later. Then we're going to have our basis spectra and wavetable, or also called wavetables. So we're going to pick 3 of them for today's example, and for each one of an envelope. Each one of them has a different amplitude envelope. They change over time to get the time-varying spectrum. You can do fixed wavetable synthesis, basically just you can synthesize a whole sound with just these 3 wavetables, so you need 3 phase oscillators, and that gives you the reconstructed sound. So, a genetic search is employed to pick a small number of spectra. Or genetic algorithm, genetic search, same thing. We're going to use that to pick a small number of basis spectra, with which the whole sound will be synthesized. So basically, by a time-varying mix of these 3, we're going to synthesize a whole sound. Each basis spectrum will have its own amplitude envelope. Yeah, so time-varying spectrum results. Okay, so what is genetic search? For those of you who have not done genetic searches before, this is a useful thing that you're likely to come across other times in your career, even if you're not just doing music. So, what is the goal of a genetic search? Genetic searches work well if you have a problem where there are probably many good solutions, but you want to find one of them. And you don't even particularly care which one of them, as long as it's one of the good solutions, that's good enough. So for instance, in this problem, what are we doing? Well, we want to find 3 frames or 3 grains or 3 spectra, however you want to think of them. We want to find 3 basis spectra, 3 little parts of the sound that we can use to represent the whole sound. So this is important. The genetic search is useful for a search space where there's many maxima. So if you think of the search space and you're just doing hill climbing, one of the problems is if there's many maxima, you're just going to climb the local hill and you're going to find a local optimized good thing, but there might be a much higher peak and a much better solution elsewhere in the search space. The genetic algorithm has enough randomness built in that it is good at finding one of the tall peaks. There might be many tall peaks, but at least you'll find one or several of them. How does a genetic search work? Well, okay, we're going to start, we use these words genetics, and we're going to talk about populations and individuals. Well, an individual is just a bit vector. But, saying bit vector is kind of boring. So we're going to call them individuals. And then we manipulate these bit vectors. But rather than just manipulating bit vectors, that's kind of boring. We want to make engineering sound more interesting, so we call it mating. We also talk about mutating. So sex and mutation, so that's much more interesting than manipulation of bit vectors. So if you don't like the words, just bear with me. I'm using standard words for genetic search. The idea is always the same, just more interesting words. So you generate a random population at the beginning of the genetic search. What does that mean? Well, each individual is just a bit vector. So you generate a whole bunch, maybe 10,000 or so, random bit vectors. You just do random bits in them. So you basically start with a totally randomized population. Now, this is the one part, the next step here is the one part of a genetic algorithm that you have to customize for whatever problem is at hand. That's one of the reasons I really like genetic algorithms in my work, both as consultant and as in music, because you have this one place. You only have one subroutine you need to change whenever you're doing a new problem or a different kind of problem. So what is that? Well, you've got this fitness function. So what's the idea of a fitness function? The idea of the fitness function is you give it one individual, one bit vector at a time. And for each bit vector, it tells you, this one's this good. It gives you a fitness or a how good is it value. Say 0 to 1, just for fun. So 0 is really bad and 1 is really good. So it just gives you an evaluation of the individual, a one-dimensional evaluation of the individual. So you can write a fitness function. Basically, your job in a fitness function is to figure out, well, okay, for this bit vector, how good a solution is it? And you give it a score between 0 and 1. So each individual gets evaluated with a fitness function that you specially wrote. And then you select the best individuals for mating. So the ones that have the best fitness, they get to mate. For the half of the population, usually I'm saying half, you can change these parameters, but it seems to work about the same even with different values. If you take half the population now, the normal thing here would be to say you do the fitness function on all the individuals, and the half that the ones that are below average in fitness, you just kill them all off. See, that makes it exciting too. That's very Darwinian. They're not surviving. They're not the fittest. So you get rid of the all of the individuals that are below average fitness. And then the ones that are above average fitness, well, now you have to rebuild the population. You got this lower half of the population. So you randomly select between good individuals, 2 good individuals for mating. And what does mating mean? Well, all you do is you take the 2 individuals, you keep the 2 parents, the 2 individuals that you randomly picked, but then you pick a random point within the bit sequence. Say you have in our example, we're going to have a 21-bit individuals. Well, so if the bit vector is 21 bit long, you pick a random number between 1 and 20. And at that point, you take, say you picked 14. You take the first 14 bits from the one individual and then take the remaining bits from the other individual, Frankenstein those two bit streams together, those two bit vectors together, and make a new bit vector. So the offspring, the result of the mating, is going to be some part of the one parent and some part of the other parent, just randomly selected. So that's what mating is. Then you've also got this mutation. Mutation, well, you just take an individual, you keep the original individual, because, you know, all of them are pretty good fitness now. You got rid of the below average fitness ones. And you make a new individual just by flipping a bit at random. You randomly pick which bit and flip it. So that gives you a new population. So you get back to, say, 10,000 individuals or however many you want in your population. That's what you do. And then you check, well, am I done with all my iterations? Am I at my maximum generation? You're probably going to have about 10,000 generations or so. So you just keep looping. You go through this whole process like 10,000 times, and what you'll end up with is individuals that are a pretty good solution to the problem. Now, if this doesn't make sense to you yet, please listen to the rest of the lecture, but also please email me before today so that I can answer questions in the next lecture. If you prefer, you could also ask about the lecture on Piazza. All right. So the size of the population is typically chosen to be hundreds of thousands of individuals. 10,000 is often enough, but hundreds of thousands is good. It sort of depends on how complicated your individuals are. This example we're doing today is very cleverly encoded. It's not going to have that many individuals, so 10,000 individuals is plenty. Each individual is a string of bits, or a bit vector. Each generation keeps only the individuals with the best fitness and kills off all the ones with below average fitness. Thus, the population is kept constant by creating new individuals by mating. And mutating also, mating and mutating. Mutating means you flip a random bit in one individual to create a new individual. So you have two ways of creating new individuals, either by Frankensteining together parts of two other good individuals, or by taking one and flipping a bit. The only part of the genetic search that knows what the bits mean is the fitness function. So this is important and a bit confusing. This is different than other searches that you'll have studied. The meaning of these bit vectors is totally unknown to everything in this program here, everything in this flowchart. None of this knows what does the individual even mean at all, except this one thing, the fitness function that you wrote, special for the problem. But otherwise, the bits are all treated equally. All these manipulations, all the crossing, mutating, has no idea what the bits actually represent. The only part of this that has any idea of what it means is the fitness function. And this is supposed to be kind of like genetics, right? If you have some genetic encoding and you have a random mutation, that random mutation isn't directed at one particular spot. You know, the random mutation just happens, and, well, probably the mutation isn't good, and it's not good for the gene. But if you're lucky, it actually makes some sort of useful change. Okay, so only part of the genetic search that knows what the bits mean is the fitness function. The fitness function is the only part of the genetic search that needs customized programming. And those are two really important things, making this genetic search something that's interesting for today's topic, but also something to remember and easy to implement, easy to use in your future work, in music or elsewhere where you might have a problem space like this, where there's lots of good solutions, you just want to find some of them. It says here the genetic search is typically run for a few million generation. A few thousand is actually enough for the example we're doing, so I think I estimated a bit high there. All right, next page. The top of this next page is a graphic or is a copy of the chalkboard that I did the other semester. And so here you have the sound that starts here, and it's got this repeating waveform. This is, of course, just drawn freehand on the board, so take it all with a grain of salt, but it's just trying to show the idea. Here you have a 2-period window. We call that frame number 1. Then half overlapping, as we always do in short window method, frame number 2, frame number 3, frame number 4, all the way up. Okay, so each two-period window we call a frame. Musicians also sometimes call these grains, a windowed part of a thing, but we'll call it frames for today's lecture. Now, you can think of the frame two ways, and it's really important that these are two different ways of thinking of the same thing. You know, you think of time domain and frequency domain, and, well, they're counterpart to each other. And so here, you can think of each frame as a time domain samples that comprise the frame, or you can think of them as the harmonic amplitudes of all the sine waves in that frame. So in time domain or in frequency domain. So when we talk about basis spectra, that's the same as talking about basis functions or basis wavetables. They're the same thing. In one case, the name sort of reflects thinking about it in frequency domain, and the other case it reflects thinking about it in time domain. Then, what we're going to do today in this example is we're going to choose 3 frames to represent the whole sound. These 3 frames are called 3 basis spectra or 3 basis functions, again, depending on whether you're thinking of them in time domain or frequency domain. Okay, coding of an individual. So, an individual in this population is a bit vector. Now, in our application, we have 3 basis spectra that we want to find. And just for discussion here, we're going to talk about 32 harmonics in each, that we analyze for each of these 2-period windows. We're going to figure out 32 harmonic amplitudes, and we're going to have 128 frames, or 128 of these windows. These are realistic numbers. In fact, the sound examples you hear today are from this. If an input has more than 128 frames, which might be common, you might have longer notes, but you can reduce that to 128. You can always keep this encoding, and it seems to have worked well for us. Just pick the first 64 frames, all of them. Keep all of the first 64, because those are really important. That's where the sound is changing a lot. That's where the onset is. Psychoacoustically, you really care about that part of the sound. And then the remaining 64, just evenly space them in the rest of the sound. Just skip a bunch of frames, but get a total of 128. Pick evenly spaced ones for the rest of the sound, and pick the first 64. Now you've got 128 frames, so this encoding will work for you, even if you have a longer node or a shorter node or what. So for this example, each individual can be cleverly encoded. I'm saying clever because you want to use few bits in the encoding. The genetic search is going to work way better if you don't use too many bits in each individual. These individuals are only 21 bits. So how are we going to encode it? This might seem obvious at first, but hey, this alternate encoding below that I'm going to talk about, the dumb encoding, is maybe what you'd think of first too. Who knows? But this is a clever way of doing it. You encode the frame number for the first basis spectrum. You're going to have to pick 3 of them. There's only 128 frames total, so you take 7 bits, 7 bits, 7 bits. First frame number, second frame number, and third frame number. So that makes a 21-bit individual. So when you generate on the previous page, when you generate that random population, hey, you get you are generating a population, maybe 10,000 different 21-bit numbers. Okay, so those are your Now, when you're generating that random population, even when you go through the genetic search and you're doing mating and mutation stuff, none of that is aware of, hey, these 7 bits, and these 7 bits, and these 7, where these bit bounds are, and where what the bits even mean. No, none of them are aware of that. It might flip the bottom bit of the 7-bit number, the top bit, or a middle bit, all the same probability. It doesn't know. The only thing that knows what these 7-bit things are, or what this encoding is, what the 21 bits mean, is the basis function. I'm sorry, the fitness function. All right. So why not encode each individual in something that, to me at least, seems more obvious, using the amplitude values for each harmonic in the 3 basis spectrum, right? we said, well, each basis spectrum is going to have 32 harmonics. So let's say we want to do 10 bits per harmonic. The problem is that it just gets to be too big in an individual, too many bits in the individual. The fewer bits in the individual, the faster the genetic algorithm is going to find you good results. If you assume 10 bits per harmonic and 32 harmonics per basis function, then we have 320 bits instead of 7 bits to describe the first basis function, 320 bits instead of 7 bits to describe the second. Think about that and stop the video now if it doesn't make sense. Think about, what am I saying here? That instead of having 7 bits to describe it, if you do it this way, where you're encoding the actual harmonic amplitudes, you have 320 bits instead of 7 bits. This is much more clever. 7, much smaller than 320. So yeah, so you would end up, if you use this kind of encoding, you'd end 960 bits per individual, and that's getting to be big. Even if you run for 1 million generations, man, you're gonna have trouble finding a good result. And plus, why do it? This has the same information in it, right? The fitness function can figure out, once it knows the 7-bit number, it knows which basis function is, it can figure out what the harmonic amplitudes are. So there's no reason to encode it this way. Use the shortest encoding you can. All right. So the fitness computation, how will that work? So here we are. This is this fitness function you have to write, but it's very important to realize that in this example here, we're going to use this least squared fit matrix function, and this is provided by standard math matrix subroutines. You do not have to write this. So even though you have to write the fitness function, there's actually very few lines of code that, for this particular example anyway, that you would have to write. So what are you going to do? Inside the fitness function, you want to see, well, how good, you have an individual given to you, and this individual represents 3 different basis spectra. So you want to do an evaluation. Well, how good a representation are these 3 spectra for the overall sound? Sometimes, if you pick them from different parts of the sound, maybe it's a pretty good representation, or maybe it's really poor. Maybe there's some parts of the sound that no combination of these 3 will represent well. So what do? You do this least squared fit, okay? And this is a matrix library. Let's talk about what AW approximates B, what that means. Well, the B here, this B matrix in your fitness function, you're going to call a matrix subroutine, and you got to set up these matrices. The B matrix that you're going to set up has all of your analysis data in it, okay? So you have 128 frames, and each one of them has 32 harmonics. So this is all of your analysis data, right? It's not the time domain samples, it's the spectra, but these are all the spectra that you analyzed. Make sure you understand what that is. That's all your original data. Now, you want to approximate that using 3 basis functions. So A here is the 3 basis functions, right? You got 3 columns, and those are the 32 harmonics. The first column is 32 harmonics for the first basis function. Second column is 32 harmonics for the second basis function. Third is 32 harmonics in the third basis function. Okay? So you have to fill in, before you call the matrix math subroutine, you have to fill in your B matrix and your A matrix. B matrix, well, that's just all the data in the analysis. A matrix depends on the individual. You pick apart those 7-bit fields, you figure out, okay, which ones are they, you fill those in there. Now, what the subroutine does for you is it figures out this W matrix for you. What this W matrix is the amplitude envelope. It has 3 rows. The first row is all 128 amplitude values for this first basis function. Second is 128 amplitude values for the second basis function, and third row is amplitude envelope for the third basis function. So what is this saying? Well, these are amplitude envelopes on your 3 wavetables, or in your 3 basis functions. And these amplitude envelopes give a different value for how much of the first wavetable, how much the second wavetable, how much the third wavetable at the first point in time to approximate your spectrum at that beginning of the sound. And then later in the sound, at every point in the sound, how much of each one of these wavetables are you going to do, how are you going to mix them to best approximate this point in the sound, this point in the sound, so forth, all 128 spectra in the sound. Again, stop now and think about this before you go on if it doesn't make sense. So this has to be an approximation. This can't be exactly equal because there's a heck of a lot less data here than here, right? All you've got is your three basis functions. This is determined by the individual, and the amplitude envelopes here. It'll never exactly match this data, but you can approximate it. Now, what this subroutine gives you is it gives you not only an error value, or how poor is it, how big is the error, which you can convert to fitness by just inverting it if you want. But you can also, it will also give you all the amplitude envelopes. So if you have a good individual, these are the best, by least squares, these are the best amplitude envelopes you can use to mix those three basis functions. So this fitness function is great because it does two things for you. It tells you the fitness, which you need just for the genetic algorithm. And then once the genetic algorithm is done, it tells you all of the amplitude values for the amplitude envelopes. All right. So, I don't know if you can hear the frogs. Earlier there was a woodpecker. Lots of different birds out. That's very nice. Okay. So, here is additive synthesis using complex basis functions. This is the last page of this. Here's a genetic synthesis using chemosymbolic sound. We don't, within the Eden matrix, we don't have this kind of synthesis. So these examples are taken from the chemo system. But what you can see here is this is during a sound. In fact, I think this is a trumpet tone. Maybe it's trombone, I don't know. That's trombone. But you can see it's very slowly changing. Once you're past the onset of the sound, this isn't a fixed waveform. And if we're totally fixed, your ear picks up on that pretty quick. It's just too static. But it's slowly changing. And if you look at it very closely on your sheet, you can see that the waveform doesn't stay exactly the same. Why is it changing over time? Well, because you're taking different mixes of the three basis functions. So if you look in the symbolic sound data file, actually, that keeps track of this, what's in there? What will you find? Well, the first thing is the first basis function. These are the samples for it. These are the samples for the second basis function, and these are the samples for the third basis function. So that's kind of cool. Those are the three basis functions. Now, so basically, those are the samples you got to stick in your wavetable. 512, or 4,096 samples, I think, is what they keep for each one. You just need enough for 32 harmonics, really. But there you go. And then what you got over here? Well, these little things here, this is three amplitude envelopes. This is for the amplitude envelope for the first basis function. These are 4,096 points. Well, we only have 128 points here, so it looks kind of small. But this is just, this is just showing what's inside this file that's doing the genetic, after the genetic algorithm is run. So here we have the amplitude envelope for this first one. Then we have the amplitude envelope for the second one and amplitude envelope for the third one. Finally, there's one shared frequency envelope. When these three phase oscillators run to synthesize a sound, all three of them have exactly the same frequency envelope. And that's very important. You don't want them to be at different frequencies. Then you get constructive and destructive interference between the harmonics. But if they have exactly the same frequency envelope, then you don't get that. One thing that's interesting to see here, if you are humanly trying to, as a human trying to make different mix functions, you might have one that jumps around like this. But look at here. Here it's negative amplitudes. It actually turns out that subtracting some of the stuff in this spectrum from this gets you a better match for a while here. And here's one, you can tell this one is pretty strong throughout the sound. And this one is differences between the beginning and the end. And this one, again, is stronger in the end. But it's kind of interesting that you would end up with negative amplitude envelopes. Something a genetic algorithm would do, but probably a human wouldn't. Okay, so I will play you these examples over the frogs and stuff. You can probably hear them, but I also have them in an email to you, which is probably clearer than this. let me grab my laptop here, which is, of course, is falling asleep. See if it'll do this for me. Yeah. Okay, so what I'm going to play you first is the original, an original C trumpet. And again. Now I'm going to play it. I don't know if the frogs, I don't know how they pick up on the microphone. If this isn't working, then use the files I sent you instead of this. Here is the synthesis with just one wavetable, and it's very plain. I mean, other than that, you just heard the trumpet. It would, if this sounds good, you're imagining it. This is much improved already because there's some time varying aspects to it. This is with 3 wavetables. And finally with 5. All right, so yes, this isn't as good as full additive sine wave synthesis, but remember, in full additive sine wave synthesis for this pitch, you would have hundreds of sine wave generators. Well, maybe not hundreds, 160 maybe, sine wave generators, where here we've just got 3 wavetables or 5 wavetables. So this is a much, much cheaper algorithm. And yes, it doesn't have as good quality as the most expensive algorithms out there, but still, for an inexpensive algorithm, it's kind of cool. So there is something I want to point out that's also kind of cool about this. Ignore about the final project unless we get back into the lab. If we do get back into the lab, I doubt that will happen this semester, but then you do want to think about, well, what would be fun to work on? What would you like to do there? Keep watching the videos about the lab that were assigned on the Tuesday handout. But I do want to say something about morphing too, and I'll play you an example of that. You can morph with these kind of wavetables. You can play 2 different GA synthesized sounds at the same time. So say you had, the example I'm going to play you is 2 different trombone notes analyzed at different pitches, but they're 2 different notes, and you just play them exactly at the same time. If you play them back, all those wavetables at exactly the same frequency, hey, you don't get constructive or destructive interference, right? All the 6 oscillators, 3 for the low note, 3 for the high note, or originally high note and originally low note, if you change them all to have the same frequency as each other, then they'll be phase locked. There won't be any, or frequency locked. There won't be any constructive and destructive interference. So basically, your ear can't tell that there's 2 timbres playing. So instead, because there's no constructive and destructive interference by the time you've gone through this wavetable playing, all the harmonics are exactly the same. So instead of a mix, instead of hearing 2 different sounds playing at the same time, say for instance there were different instruments, for a more obvious example. Say you were playing a violin and a flute at the same time. Well, even if they're equal volume, if you play them at the same time, if you play a recording back, well, you hear a violin and a flute playing at the same time. You don't hear something halfway between a violin and a flute. But that's because of constructive and destructive interference. In this wavetable stuff, in this additive synthesis, you're using these complex basis functions or these wavetables. At that point, you're not getting constructive and destructive interference because they all have the exact same frequency envelope. So I'm going to play you an example here. In this example, there's a low trombone note and a high trombone note, and then I just played up a scale. You hear a gradual timbre change as you go up the scale. There's not a sudden timbre jump, but it's a gradual timbre change because basically when you're playing the low note, I use all the information from the low notes analysis. When you're playing the high note, all the information from the high note analysis. But in between, I play a mix of the 2. So I'm playing 6 phase oscillators and mixing them, and let's see, here we go. So you're going to hear low note and high note. Now this trombone player, actually he is now dean at, where? at Purdue, I think. But anyway, he was a student of mine long ago, and if you don't like his trombone playing, well, he didn't go on to be a professional trombone player, so it's okay. Here you go. So those are the two original notes. So that was probably not the most amazing recording you've ever heard, but keep in mind, I'm not a very good player, so so I didn't add anything to it, and also this is an inexpensive synthesis technique, but it should have been interesting. You can play it again using a better recording. It should be interesting just to listen how you do get a time varying spectrum out of it, and you know, there's not a sudden timbre jump or anything. So I'm trying to figure out if I can show you a video here without without too much glare. Seems unlikely. Okay, let's see if I can turn up my brightness. Okay, I'm going to give up on this. So what I would like you to do is listen to this other video linked at the end of the come on, baby. Yeah, so this is a cinematic production. I'm going to give you some of the text here, which is almost impossible to read. This is Cuckoo. He's a online YouTuber, and he says, I'm currently finishing work on an animated short. I'm done with the animation and now working with the soundtrack. I've long thought about using continuing fingerboards as an important part of the soundtrack, and now I'm finally beginning to see where it fits in. This is just improvisation. It's a necessary part before finding the balance between melody, story, mood, and letting the film speak without the music getting in the way. So this is something interesting I wanted to show you, not related to today's topic so much, but just I wanted to give you an idea of what it's like to work in a one-man studio making an animated film. Cuckoo, or his given name is Andreas Paleologos, lives in Norway, I believe, and he drew all of the background watercolors. He did all the animation. He did everything, and here you can see him doing the music. And you should see this online because you'll see a lot better. You see a screen up there on the left. He's following along with the movie he's doing, improvising. So it's just something to think about. If you are multi-talented, that you can actually produce like whole movies yourself in your own studio at home. Anyway, just something I wanted to show you. Thank you. We'll see you next time.